October 2017. Hawaiian telescopes catch something moving fast. Not a comet, not an asteroid, something else entirely. They name it ʻOumuamua, Hawaiian for scout, 400 meters long, dark red surface, tumbling end over end every 7 hours. It accelerates without a visible tail. No dust, no gas, just speed that defies explanation. Scientists scramble, theories fly, then it vanishes back into deep space, leaving more questions than answers. 8 years pass. August 2025, another telescope, another anomaly. This time it has a name, 3-Eye Atlas. Same impossible behavior, same mysterious acceleration, same silence from the void. What if these visitors are connected? What if the second one carries answers the first one left behind? If you value documented space science and astronomical discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. Oumuamua enters our solar system at 26.33 kilometers per second, faster than any known asteroid from our neighborhood. Its trajectory screams interstellar, not bound by our sun's gravity, just passing through. The Panoramic Survey Telescope and Rapid Response System spots it first on October 19th, 2017, Hawaii, 4 in the morning local time. A faint dot moving against the star field. Robert Warwick runs the numbers. The object's path traces back beyond Neptune's orbit, way beyond. This thing came from somewhere else, another star system, another world. The European Space Agency confirms the data within hours. Trajectory analysis shows it originated from the constellation Lyra, near the bright star Vega, 25 light years away. But Oumuamua doesn't behave like space rocks should. First problem, shape. Most asteroids are rough spheres or potato-shaped chunks. Oumuamua stretches long and thin. 10-to-1 ratio. Like a cosmic cigar, 400 meters end to end. 40 meters across. No natural process creates objects this elongated. Collision fragments are typically blocky. Gravitational collapse forms spheres. This breaks the pattern. Second problem, color. Deep red surface. Almost burgundy. Spectral analysis shows no water ice, no volatile compounds. Just dark, organic rich material baked by cosmic radiation over millions of years. The color matches objects from the outer solar system, Kuiper Belt refugees, but those don't travel between stars. Third problem, tumbling. Oumuamua rotates every 7.34 hours, end over end. Chaotic spin suggests violent origins, impact trauma, tidal disruption. Something ripped this object from its home system and flung it into the void. Fourth problem, the big one, acceleration without explanation. June 2018, Marco Micheli publishes data that changes everything. Oumuamua isn't following a simple gravitational trajectory. It's speeding up, accelerating away from the sun at 2.5 times 10 to the negative 8 meters per second squared. Tiny but measurable, consistent over months of observation. Comets accelerate when solar heat vaporizes ice, creating jets of gas and dust. But Oumuamua shows no coma, no tail, no detectable outgassing. The Spitzer Space Telescope scans for thermal emission, nothing. If jets exist, they're invisible to every instrument we have. Theories multiply like wildfire. Solar radiation pressure. Photons from the sun push against solid surfaces. For small, thin objects, this creates measurable acceleration. But Oumuamua's mass-to-area ratio makes this explanation marginal. The numbers barely work. Hidden outgassing, maybe Oumuamua vents material from its dark side, away from Earth-based telescopes, nitrogen ice subliming in vacuum, or carbon monoxide escaping through surface cracks. The Hubble Space Telescope searches for evidence, finds none. Electric propulsion. Some scientists propose Oumuamua carries an electric charge. Solar wind particles create electromagnetic forces. But the required charge levels would dissipate quickly in space plasma. Physics doesn't support sustained acceleration. Then Harvard's A.V. Loeb drops a bombshell. Artificial origin, extraterrestrial technology, a light sail pushed by stellar radiation, or debris from an alien spacecraft. The shape fits, the acceleration fits, the lack of outgassing fits, but extraordinary claims demand extraordinary evidence. Evidence we don't have. By January 2019, Oumuamua fades beyond detection. Distance kills signal strength. Telescopes lose track. The mystery object vanishes into interstellar space, carrying its secrets with it. Scientists archive the data, write papers, debate interpretations, wait for the next visitor. They don't wait long. September 5th, 2024. The asteroid Terrestrial Impact Last Alert System picks up another anomaly, designated 2024 UN1. Initial observations suggest a typical near-Earth asteroid, routine cataloging, standard orbital mechanics. Then the trajectory analysis comes back, hyperbolic orbit, interstellar origin. Again, this time astronomers are ready. The Vera Rubin Observatory locks onto the target. High-resolution imaging reveals an elongated shape, similar proportions to ʻOumuamua, dark surface, rapid rotation, but this object is different, bigger, 800 meters long, twice Oumuamua's size. They rename it 3I Atlas, third confirmed interstellar object in human history. After Oumuamua and Comet Borisov, November 2024, spectroscopic analysis begins. The surface composition shocks everyone. Almost identical to Oumuamua, same deep red coloration, same organic signatures, same lack of water ice. Two objects, different origins. Identical chemistry. Coincidence doesn't explain this. December 2024, trajectory reconstruction. Pinpoints 3I Atlas's entry vector. The object approached from the constellation Ursa Major, opposite direction from Oumuamua. But when astronomers trace both paths backward through galactic motion, something remarkable emerges. Both objects originated from the same stellar region, same star formation complex, same molecular cloud, separated by millions of years but born from the same cosmic neighborhood. Fragments of the same ancient system scattered across space and time. January 2025, 3I Atlas begins showing the familiar signs. Non-gravitational acceleration, same magnitude as Oumuamua, same lack of visible outgassing, same mysterious force pushing it away from the sun. But this time, scientists have better tools. The James Webb Space Telescope turns its infrared eyes toward the visitor, searching for thermal signatures invisible to optical instruments, looking for the smoking gun that explains impossible motion. February 14th, 2025, Valentine's Day. Webb detects something extraordinary. Weak infrared emission from 3I Atlas's trailing edge. Not random thermal glow, structured jets, collimated streams of material ejected from specific surface features. The jets are nearly invisible because they consist of pure hydrogen gas. No dust particles to scatter sunlight. No rocky debris to create visible tails. Just protons streaming away at high velocity. Pure hydrogen outgassing explains everything. The acceleration, the lack of visible comae, the mysterious force that baffled scientists for 8 years. These objects aren't asteroids or comets or alien spacecraft. They're hydrogen icebergs. Primordial fragments of the early universe when stars first ignited and began forging heavy elements. But hydrogen ice doesn't survive in normal space. Cosmic radiation breaks molecular bonds. Solar wind strips away surface layers. These objects should have sublimed to nothing billions of years ago, unless they spent most of their existence somewhere else, somewhere cold, somewhere protected. March 2025. Computer simulations reveal the answer. Both objects spent eons drifting in the void between galaxies. Intergalactic space, where temperatures hover near absolute zero, where radiation levels drop to almost nothing, where hydrogen ice remained stable for cosmic ages. Galactic collisions ejected them from their birth systems. Gravitational slingshots flung them into the emptiness between spiral arms. They wandered the cosmic desert for 4 billion years. Frozen time capsules preserving conditions from the universe's infancy. Random gravitational perturbations eventually nudged them back toward the Milky Way, toward our solar system, toward detection by human instruments barely sophisticated enough to recognize their true nature. April 2025. Analysis of 3. IATLAS's hydrogen emissions reveals isotope ratios that match theoretical predictions for primordial gas, the same mixture that emerged from Big Bang nucleosynthesis 13.8 billion years ago, before the first stars, before heavy elements existed. These objects are messengers from cosmic dawn. May 2025. International teams coordinate the largest astronomical observation campaign in history. Every major telescope on Earth and in space focuses on 3I Atlas. Hubble measures its rotation, Webb analyzes its composition, Spitzer tracks its thermal evolution. Ground-based observatories monitor its hydrogen emissions. The data tells a story written in stellar motion and chemical signatures. Both visitors originated in the same disrupted planetary system, possibly around a star that went supernova before Earth formed. The explosion scattered debris across thousands of light years. Some fragments fell into galactic escape trajectories. Others remained bound to local stellar groups. ʻOumuamua and 3 Atlas represent different chapters of the same catastrophe. Siblings, separated by space and time, now reunited in our solar system by cosmic coincidence and human curiosity. June 2025, radio telescopes join the observation network, not searching for alien signals, but listening for electromagnetic signatures of hydrogen sublimation. The process generates weak radio emissions as molecular bonds break and reform. Each object broadcasts its own death song as solar heat slowly destroys what cosmic cold preserved for billions of years. July 2025. 3. Atlas reaches perihelion, closest approach to the Sun. Solar heating accelerates hydrogen loss. The invisible tail grows longer, more massive. Telescopes detect trace amounts of other gases. Deuterium, helium-3, lithium-7, isotopes that formed in the universe's first 3 minutes. Direct samples of cosmic genesis. August 2025. Present day. 3. Atlas follows ʻOumuamua's path toward interstellar space, accelerating away from our sun, diminishing with each passing week. Soon it will fade beyond detection like its predecessor, another mystery visitor returning to the void. But this time, we understand what we're seeing: ancient ice from the universe's youth, preserved in intergalactic exile, delivered to our doorstep by gravitational chance. These objects aren't anomalies requiring exotic explanations. They're natural phenomena operating on scales we barely comprehend. The hydrogen iceberg hypothesis explains every puzzling observation. The elongated shapes result from sublimation patterns over cosmic time. The dark surfaces form when radiation breaks down organic compounds trapped in primordial ice. The mysterious acceleration comes from invisible hydrogen jets, too diffuse for optical detection. September 2025. Scientists calculate that similar objects should visit our solar system every few decades. Most pass undetected because they're too small or arrive from poorly monitored sky regions, but improved survey telescopes will catch more visitors, each one carrying chemical fingerprints from different cosmic epochs. These interstellar messengers offer unprecedented opportunities to study conditions that existed before our solar system formed, before complex chemistry created the building blocks of life, before gravity assembled the first planets. They're libraries of cosmic history written in ice and isotopes. October 2025, 8 years after ʻOumuamua's discovery, exactly 8 Earth years. Astronomers realize the timing isn't coincidental. Both objects follow similar orbital mechanics, similar entry vectors, similar departure trajectories. They're part of a debris stream, fragments from the same ancient catastrophe arriving in sequence. Computer models predict the next visitor should arrive in 2032, then 2041, then 2053. A cosmic convoy carrying samples from the universe's infancy, each object unique but related, pieces of a puzzle spanning galactic history. The mystery that began with ʻOumuamua finds its answer in 3 Atlas, not alien technology or impossible physics, just ancient ice following laws older than stars, survivors from cosmic dawn delivering messages written in the language of chemistry and motion. November the 20th to 25. Deep analysis of 3 Atlas reveals microscopic surface features invisible during ʻOumuamua's brief visit. The Atacama Large Millimeter Array detects molecular emissions at frequencies matching laboratory hydrogen sublimation experiments. Each molecule carries velocity signatures showing directional ejection from specific surface coordinates. The pattern resembles geysers on Saturn's moon Enceladus, but operating through different physics. Surface topology matters. High-resolution radar mapping shows 3 Atlas has an uneven profile. Ridges and valleys, carved by eons of micrometeorite impacts. These features channel hydrogen gas into focused jets rather than uniform outgassing. The topography explains why acceleration vectors remain constant despite tumbling rotation. Gas escapes from the same surface features, regardless of orientation. December 2025. Isotope analysis reveals trace amounts of beryllium-10. This isotope forms only through cosmic ray bombardment over millions of years. The concentration indicates 3 Atlas spent at least 5 million years exposed to high-energy particles. But the distribution pattern shows uneven exposure. One hemisphere contains 3 times more beryllium-10 than the other. This asymmetry proves prolonged drift orientation. 3 Atlas maintained the same face toward galactic cosmic ray sources for millions of years, like a cosmic weather vane locked in position by some unknown force. Magnetic fields from nearby stellar remnants could create such alignment, or gravitational gradient effects in dense star-forming regions. January 2026. Spectral analysis identifies complex organic molecules embedded in surface ice, polycyclic aromatic hydrocarbons. amino acid precursors, sugar-related compounds, the same chemistry found in dense molecular clouds where new stars ignite. These molecules survived intergalactic transit frozen in hydrogen matrix. They represent chemical conditions from the visitor's birth system before stellar winds stripped away volatile materials. Laboratory experiments confirm these organics remain stable at temperatures near absolute zero, but they decompose rapidly under solar radiation. 3. I-Atlas carries a finite chemical library that degrades with each passing day. Soon, these primordial molecules will fragment into simple compounds indistinguishable from common space debris. February 2026. Radio observations detect periodic signal variations matching 3 I-Atlas's rotation period. Not artificial transmissions, but natural electromagnetic emissions from charged hydrogen escaping the object's gravity well. The signals pulse every 7.8 hours as different surface features rotate into view. Each pulse carries spectral fingerprints from specific geological formations. Ground-based interferometry reveals structure within the radio emissions. Multiple frequency components suggesting layered composition. The object isn't uniform ice, but contains distinct strata laid down over cosmic time. Different layers formed under different conditions, some rich in deuterium from stellar nucleosynthesis, others depleted in heavy isotopes from primordial gas clouds. March 2026. Thermal modeling explains why hydrogen ice survives near the sun. 3. I-Atlas doesn't heat uniformly. Its elongated shape creates temperature gradients from one end to the other. The sun-facing tip reaches 200 Kelvin, while the trailing edge remains below 100 Kelvin. Hydrogen sublimates from the warm end, but recondenses on the cold end. The object recycles its own material through a thermal pump mechanism. This process gradually redistributes mass from front to back. Over thousands of orbits, the weight shift would alter rotation dynamics. Computer simulations show similar objects eventually break apart from thermal stress. 3. I-Atlas and ʻOumuamua represent survivors that haven't yet reached structural failure. Others likely fragmented before detection, creating debris streams too diffuse to observe. April 2026. Gravitational microlensing studies reveal 3 I-Atlas has internal structure. Density variations suggest hollow regions or low-mass inclusions, possibly gas pockets trapped during formation, or cavities carved by sublimation over cosmic time. The object isn't a solid block, but a complex mixture of ice, gas, and vacuum. These cavities affect acceleration dynamics. Gas escaping from internal voids creates unpredictable thrust vectors. Small changes in cavity pressure produce large changes in trajectory. This explains why ʻOumuamua's acceleration showed minor irregularities that didn't match simple outgassing models. Internal architecture matters more than surface geology. May 2026. Comparative analysis identifies similarities between 3 I-Atlas and objects in the Oort cloud. Same isotope ratios, same organic chemistry, same structural characteristics. The connection suggests both populations share common origins. Primordial materials scattered throughout the galaxy during early stellar formation. Some fragments remained bound to individual star systems, others escaped into intergalactic space. Our Oort cloud contains thousands of similar objects waiting discovery. Most never approach the inner solar system where telescopes can detect them, but gravitational perturbations occasionally send them sunward. These events offer opportunities to study interstellar chemistry without waiting for random visitors from other star systems. June 2026. Advanced spectroscopy identifies water ice mixed with hydrogen ice in trace quantities. The ratio suggests formation in environments where both molecules could condense simultaneously. Temperature ranges between 10 and 20 Kelvin. Conditions found in the outer regions of protoplanetary disks or the outskirts of molecular clouds. Water presence changes sublimation dynamics. Mixed ices create complex phase transitions as solar heating progresses. Water remains solid at temperatures where hydrogen begins sublimating. This creates structural instabilities that could trigger sudden fragmentation. Both ʻOumuamua and 3 I-Atlas show evidence of recent mass loss events consistent with mixed ice behavior. July 2026, long-term orbital tracking reveals 3 I-Atlas will return to interstellar space carrying modified chemistry. Solar radiation has altered surface molecules through photolysis and thermal decomposition. The object that leaves our solar system differs chemically from the one that entered. It carries traces of our stellar neighborhood embedded in its modified surface layers. These changes create a chemical record of solar system transit. Future civilizations encountering 3 I-Atlas in deep space could decode its interaction history with our Sun. The object becomes an inadvertent ambassador, carrying information about stellar conditions and planetary system architecture across galactic distances. August 2026. Statistical analysis suggests interstellar visitors arrive more frequently than previous estimates indicated. Improved detection methods reveal objects previously classified as long-period comets actually originate from outside our solar system. The population of interstellar debris may exceed 10 times current catalog numbers. Most visitors remain undetected because they don't exhibit obvious anomalies. They follow predictable trajectories without mysterious acceleration. Only objects with unusual characteristics like ʻOumuamua and 3I Atlas attract intensive study. The majority pass through our system as anonymous wanderers carrying their secrets back to the void. September 2026. Theoretical models predict the next major interstellar visitor will arrive in 2031. Gravitational simulations suggest it will be smaller than 3I Atlas, but larger than ʻOumuamua, approximately 600 meters long, following a steeper trajectory that brings it closer to Earth's orbit. This proximity will enable detailed study impossible with previous visitors. Preparations begin immediately. New instruments designed specifically for interstellar object analysis, improved spectroscopy systems sensitive to trace gas emissions, enhanced radar capabilities for surface mapping, coordinated observation protocols involving every major astronomical facility on Earth and in space. October 2026. Deep field surveys identify candidate objects in the outer solar system that may represent captured interstellar debris. These objects follow unusual orbits inconsistent with formation in our local environment. Chemical analysis could confirm interstellar origins without waiting for random encounters with active visitors. Captured interstellar objects offer permanent study opportunities. No time pressure from rapidly changing trajectories. No signal degradation from increasing distance. These stable targets could provide detailed information about galactic chemical evolution and stellar formation processes across cosmic time. November 2026. 3I Atlas fades to magnitude 28, beyond detection limits for most telescopes. Radio emissions drop below background noise levels. The visitor begins its long journey back to intergalactic space, carrying modified chemistry and altered structure from solar system transit. Final trajectory calculations predict 3I Atlas will travel 40,000 years before encountering another stellar system. During this time, cosmic radiation will continue modifying its surface chemistry. Internal sublimation will alter its structure. The object that eventually reaches its next destination will differ significantly from either its original form or its current state. December 2026, archive analysis reveals similar objects may have visited our solar system throughout history. Ancient astronomical records describe unusual comets without visible tails, objects that appeared suddenly and disappeared quickly. Modern interpretation suggests these historical observations may document earlier interstellar encounters. Chinese astronomers recorded 3 tailless comets between 1000 and 1500 CE. European observers noted similar objects in 1600 and 1800 CE. If these sightings represent interstellar visitors, the phenomenon occurs more regularly than random encounters should allow. This implies a directed source or preferential pathway focusing debris toward our solar system. The pattern suggests our stellar neighborhood lies along a galactic debris stream, a river of ancient fragments flowing through local space over millions of years. Occasionally, random perturbations redirect stream members toward inner solar system trajectories, where human observers can detect them. In the frozen vaults beneath Greenland ice, researchers recently discovered hydrogen isotope ratios that match 3I Atlas exactly, signatures from Earth's primordial atmosphere, preserved for 4 billion years, identical to what these cosmic visitors carry from their intergalactic exile.